Hi, everybody. Hopefully, the lab write up isn't too painful. Make sure you ask me questions if you need to. Chapter 6, super easy. We're still dealing with forces. We're just dealing with friction, a little bit more drag force, actually, nothing new with that one, and a little bit more uniform circular motion. And then just a couple of quick textbook and challenge problems, so get your brains thinking. This is almost all review, so this should go fairly quickly. First of all, you remember frictional force, there are two different types: kinetic between two moving surfaces and static between two stationary surfaces. It always acts against the slide or potential slide of an object. When it's, again, kinetic friction when it's moving relative to another surface. Typically, what you end up here is you could very quickly calculate mu if you measured the frictional force required to move this at a constant velocity. Given that you keep adding masses on top here to increase this normal force, you discover that it'd be fairly linear. The frictional force would tend to increase as the normal force increases. And this is typically how you would find mu sub k. Different surfaces, different combinations of surfaces produce different mu's. Where do you find these mu's? Either experimentally or you can look them up. There's tables with pages upon pages of them. Here's the formula for it. The magnitude of the force of kinetic friction is just equal to mu sub k, the coefficient of kinetic friction, times normal force. Here's a quick question. A person has a choice of either pushing or pulling a sled at a constant velocity. Friction is present. If the angle theta is the same in both cases, does it require less force to push or pull? And I'll let you think about it for 3 seconds. 3, 2, 1. The answer, of course, is that pulling it, believe it or not, will require less force. Why? Because of this vertical component of your tension is actually going to reduce the normal force here. It's going to be smaller than the case over here, where you pushing downward on it is actually going to increase the normal force. And because the normal force is larger in this case, your force of friction is going to be larger here than it is here, if that makes sense. So in this case, pulling actually reduces a couple of things. Friction, or take a quick look at this sled racing example number 1. Coefficient of kinetic friction is that. How far does the sled go before stopping? And you might say, whoa, you didn't give us the mass of the sled. This is impossible to do. Again, just a quick reminder, let's just make it a variable m. In that case, the force of gravity on it is mg. Normal force is going to be equal to mg as well. And the force of friction acting against this thing, if mu is 0.05, is going to be 0.005 times the normal force, which we know again is equal to mg. It's this net force, the force of kinetic friction, that's going to slow us down. So now if we just do F equals ma, we can calculate our acceleration. Our net force in this case is 0.0. Actually, I put too many zeros. I'm sorry. I just looked at that. 0.05 is 0.05 mg equals the mass of our object m times the acceleration. Sure enough, the mass of our object cancels, and our acceleration is 0.05 meters per second squared. Technically negative because we're slowing down. You could have also said the force was negative. How far does the sled go? Far, we're talking about distance. Just doing v final squared equals v initial squared plus 2a delta x. Our final velocity is 0. Our initial speed, they tell us up above, is 4, plus 2 times our acceleration, negative 0.05 times x, gives us 0 equals 16 minus 0.1x. Very quickly you can realize, okay, this thing should go 160 meters before stopping. Moving on, just real quick, if you put a force probe along with an object that was at rest and you just pulled on it, you would discover that you could exert more and more force without it moving until suddenly, and I know this is an experimental graph, it's kind of messy, At this point right here, is the maximum force of static friction. And the moment you exceed that, suddenly you break away, and the force that you're dealing with right here is the force of kinetic friction. Notice it suddenly drops. This is while it's sliding down here. And this line right here is when it's stationary. So pulling on it, all of a sudden, boom, and you start sliding. Yes, I realize this is a rough graph, but it's very difficult to hand pull this well. Properties of static friction. Maximum force of static friction is equal to mu sub s, the coefficient of static friction times normal force. So static friction is kind of unique. It can range anywhere between 0 up to that maximum value where the object breaks away, and then immediately it drops down to kinetic friction. So this can have a whole range of values, all between 0 up to its maximum, which is mu sub s times normal force. Coefficient of static friction is usually larger than the coefficient of kinetic friction, except in some really bizarre situations. But most of the time you can assume that's true. Take a quick look at this one. Let's make gravity 10 just to make this a little bit easier. We've got a sled. It's 35 kilograms, so force of gravity will be 380 newtons this time. Normal force 300 and also 380. And let's say we're trying to apply a force this direction. What's going to be the maximum force of static friction? Well, it's going to be 0.35 times that. I guess I still need to use a calculator. Where in this case, the maximum force of static friction, it can range anywhere between 0 up to, if you multiply mu sub s times normal force, you get 133 newtons. So what's the maximum force that can be applied to sled before it moves? The answer is 133. Technically, at that point, force static friction can still equal that. So how much force is required to actually get it to slide? The answer is 133 newtons plus a microscopic bit. Take a quick look at this one. Civil engineers have to worry about this all the time. In this case, the original slope of the material used to make this was at 45 degrees, but mu sub friction, static friction, is only 0.5. So the question is what angle do we need to reduce this by so that this thing doesn't slip? Well, if you look at it real quick, let's just take a look at this mass right here. And just do it, whoops, that's supposed to be straight down. Close enough. Force of gravity, of course, mg. If we break that into its vertical and horizontal components, you'll, of course, get this downward component. This is theta up here again, is mg cosine of theta. And this piece down here, mg sine theta. And so the normal force, of course, is equal to this component right here. So that's mg sine theta. Cosine theta. And if we want this thing to stay up here, this is the normal force, we need the frictional force, the static force of friction, to match this piece that's acting downward here. So that's got to equal mg sine theta. Well, you can very quickly calculate what mu would need to be to hold this thing in place. We know that the maximum the force of static friction can be, let me write it as max, is equal to mu sub s times normal force. In this case, let's assume that this is just at the point where it will just barely stay. So we end up with mg sine theta is equal to mu sub s times normal force, which in this case is mg cosine theta. And you can very quickly see this, I hope. Dividing both sides by mg cosine theta, mg cancels out. Sine of theta over cosine theta is tan theta. So we can actually work out, if this is actually 0.5, we can figure out what the maximum angle theta that the slope can be without it sliding. So setting it up real quick, tangent of theta equals 0.5. Grabbing your Inspire real quick and doing an inverse tangent of 0.5, excuse me for a moment, we'll discover that the steepest angle we could possibly have is only 26.6 degrees. That's the slope down here. So what angle do I actually need to remove in this case? Well, 45 minus that, or we need to remove a total angle here of 18.4 degrees to make this a safe slope. Otherwise, what would happen on a good rainy day? This whole part will simply slip. And this is what happens in avalanches and in landslides, where simply the angle becomes too steep for the friction between the layers to hold it in place. Here's another quick example. It's example number 4. So in this case, we're applying 100 newtons to this 10 kilogram mass, and it's sitting on top of, and there's some friction between it and this other thing, and it's sitting on top of a 40 kilogram object that's on a frictionless surface. It must be an air hockey table. We're given that the coefficient of static friction is 0.6 and the kinetic friction is that. So there's two options here. If the static friction is sufficient between these two, when you apply the 100 newtons, this won't slip, and instead both of these two objects will accelerate that way together. The other option is that perhaps the force of static friction is not sufficient to keep these, in which case this object is going to slide relative to the larger mass. So how do we solve that real quick? Well, without drawing all the other forces, we can realize that the normal force here is 98 newtons. And so what's the maximum force of static friction? Well, that times 0.6. Without a calculator, please forgive me if this is wrong. I get roughly 58.8 newtons. Oh, that's interesting. And the force of kinetic friction, just that times 0.4, I think is 39.2 newtons without a calculator. So what does that mean? We're applying 100 newtons here. The force of static friction acting this way is not going to be sufficient to keep this thing from sliding. So what are we dealing with? We're definitely dealing with kinetic friction. So what's going to happen here? Well, this is kind of interesting. I'm going to draw it separately. On our 10 kilogram object, we're going to have 100 newtons acting this way on it. And since we know this is larger than the maximum force of static friction between these two, that's supposed to be a kilograms. We know that we're dealing with kinetic friction acting this way, 39.2 newtons. So just using F equals ma, the net force on this thing is 60.8 newtons. I hope I did that right. Equals 10 times a. Acceleration, 6.08 meters per second squared. What about our 40 kilogram object? Well, think about this real quick. There has to be an equal and opposite reaction. This friction between the surface here is applying a force backwards on this object of 39.2. At the same time, it must be pushing forward on this thing with 39.2 newtons. Solving this real quick, looking at the big 40 kilogram object, there's only that 39.2 acting forward on it. There's no, normal force of gravity. I'm not going to draw those just to avoid confusion. So now doing F equals ma on this object, net force 39.2 equals 40 times a. Dividing that by 4, 9.8. The acceleration in this case, 0.98 meters per second squared. So this one's going to slide or accelerate more rapidly than this one. They're both going to accelerate towards the left, but at different rates. What is going to happen here, eventually this thing is going to fall off of here. And the moment it does that, then it's going to accelerate at 10 meters per second squared. And this will have zero acceleration because there's no net force. It'll just keep moving with whatever velocity it had before this thing slid off. Take a look at this one real quick. These are the classic, oh good, we've got a frictionless surface. Oh, rats. Oh, and the incliner blank and blank. Oh, shoot. I can't do this one unless I make something up real quick. The Muse are missing. Oh, let's skip this one. I've got another one coming up in just a moment. Again, just remember drag force in last chapter. Usually we use 1/2 the coefficient of drag times the density of the medium it's moving through, most time air, but it could be water, times the cross-sectional area times the velocity squared. It's an approximation, but not bad. And you can calculate terminal velocity. I'm going to go skip through centripetal force just so I can get to some of these more interesting ones. This is a real story. Diavolo, a gentleman named that, actually did or demonstrated this at a circus. My question is how fast would he need to go at the top so that he would actually stay on the track? And it's kind of fun. What has to happen here? Well, assuming he's just going barely fast enough, the only force acting on him would be gravity, mg, where he's just barely able to go around this thing. And the question is how fast. Now, if he went faster than this, then there'd have to be an additional normal force acting downward because it would require more centripetal force, and this by itself wouldn't be sufficient. So in this case, let's assume that gravity is providing all of the necessary centripetal force. So in this case, mg equals, and let's do, for the centripetal acceleration, there's lots of different equations, but v squared over r suits us well in this case. Mass cancels. So we simply end up with 9.8 equals v squared over the radius of this thing 3, or 29.4 is equal to v squared. Unfortunately, I can't do that in my head. Sorry, give me a split second. 29.4 raised to the 0.5 power. How fast he had to be going at the top of this? About 5.4 meters per second. He could go faster than this, and he would definitely stay on the track. If he went slower than this, though, his wheels would actually leave the track, which would not be ideal. Curved banks, just a quick reminder on this one. Normally, when we have objects on an incline, we always break the forces on them. Here's a car, side view, headlights, roof. Normally, when we have something on an inclined plane like this, we always break the force of gravity into its vertical and horizontal components that are parallel and perpendicular to the ramp. However, in this case, we've got an interest, or what we're going to do instead is, when you're dealing with a banked curve, the normal force here is actually larger than the force of gravity. And what we end up having here is this. If we break this into its vertical and its horizontal pieces, this piece right here of it is equal to the weight of the car, mg. And this inward piece right here is F net, or in this case, it's going to be the centripetal force necessary to keep the car going in a circular path. Up here you can sort of see a redrawing of it. Force of gravity down this way, normal force this way. If you break this into two components, this vertical component has to be equal to the force of gravity, and this piece right here is going to be equal to the centripetal force. So how do we solve this real quick? We've got a car that needs to travel at 20 meters per second around a curve of radius 90 meters, or 190 meters. What angle should this be banked at so that this works? Just a little bit of trig here real quick. This is theta. If this is theta down here, and so what can we write here? We can say the tangent of theta is equal to the opposite side, centripetal, over the adjacent side, mg. Or you can write this, mg times the tangent of theta is equal to the centripetal force. And you might say, wait a second, isn't centripetal force just equal to the mass times centripetal acceleration? Yeah. So you can also write it this way, dividing by the object's mass. For bank curves, the centripetal acceleration is just equal to g tan theta. So we can actually solve this real quick. It's a real fast problem now. We know that g times the tangent of theta has to equal v squared, in this case 20 squared over the radius, the centripetal acceleration v squared over r. And solving for theta, 400 divided by 190 times 9.81, and then the inverse tangent of that angle, we find out that our track should be banked, if I did my math right, at 12.1 degrees. All right, hopefully not a problem. Oh, and I threw in a couple of textbook problems real quick. 51 is a typical one, and so, is it frictionless? Oh, it is a frictionless plane. All right, it's all right. This is kind of simple then. There's the masses. Force of gravity is that. Breaking it into its parallel and perpendicular components, you get that. And the force of gravity on this one is that. So first of all, what's the magnitude of the acceleration? If we do part A here, our net force on this, there is a normal force up here of 31.4 newtons. So our net force is this 22.6 trying to accelerate it this way, minus the 18.1 trying to draw it that way. Sorry, I got a little blob there. So we end up at 22.1 minus the 18.1 is accelerating the whole mass of the system, which is the 3.7 plus the 2.3 all times A. Solving that real quick on my calculator, minus 18.1 divided by the sum of those two, which is 6. And I get the acceleration of the system is 0.65 meters per second squared. B, the direction of the acceleration of the hanging block. Oh, it's accelerating downward for the hanging block. And C, what's the tension in the cord? And that's where it gets a little more exciting. So we know this one's accelerating downward. So we know the tension here, pause for a moment. We could solve the tension either here or here by looking at just one block by itself. If we look at the whole system, we can't solve for tension because it's internal to the system. But let's just look at just this one block. And we know the acceleration of it, so we can solve for this. We can look at the net force on the hanging block equals its mass times acceleration. The net force in this case is 22.6 minus the tension equals the mass 2.3 times that acceleration 0.65. Solving for the tension, we end up with 22.6 minus the acceleration times the mass 2.3, and I get that the tension here is 21.1 newtons. And you would end up with the exact same answer if you solved it up here. It just takes a little bit longer. Our next problem, this is an interesting one. You've got a 49-kilogram rock climber, and she's climbing a chimney where she's pushing with her shoes here on one wall, and her back's pushing against this wall on the other side. And that she's saying, or it tells us that she's reduced her push against the rock till her back and her shoes are on the verge of slipping. In other words, we're right at the maximum, or we're just at the point where the maximum friction's acting. It says draw a free body diagram, but I'm actually going to draw it here. So let me quick talk this through before you get anywhere on this one. You might say, whoa, this is impossible. We've got two different surfaces to deal with. One between her shoes here and one between her back here. But here's the interesting part. Whatever normal force she's pushing, or the wall's pushing back with here, has to be exactly equal to the normal force acting on her back here. Why? We know there's no net horizontal force. She's not accelerating horizontally. So these two forces must be exactly equal. What does it mean? If we're right at that verge, this force of static friction here must be exactly equal to 1.2 times the normal force. It's right at its maximum value. It's just barely holding. And over here on her back, same thing is applying, 0.8 times normal force. The other forces acting on her, of course, are the force of gravity acting downward. Force of gravity in this case, her mass times 9.81. Let's just call it 480 newtons. So what do we know has to be true here? What's her magnitude? What's the, what fraction? We know that the sum of these two upward forces must be just sufficient to keep her from sliding. So in this case, we know that 1.2 times normal force plus the 0.8 times normal force has to equal 480. And you can very quickly realize, oh wait, that's 2 times n. So n has to be 240 newtons. So that's how much she's pushing on her with her shoes and with her back. What fraction of her weight's being supported by her shoes? Well, if you compare these two, the total upward force is 2n, the sum of these two. And what fraction of that is being provided by her shoes? Well, 1.2 times n. 1.2 over 2 is 0.6, or 60% of the force is being provided by her shoes, 40% by the force of friction on her back. Oh, the challenge problem. This is actually linked to the assignment sheet, but I just want to talk you through it. I'm not sure if I can even solve this one completely. In this case, just real quick, let's make gravity 10 just for sanity. So I'm sitting on the floor, force of gravity on me, 1050 newtons, normal force 1050. And I've got coefficient of static friction and kinetic friction. So the maximum force of static friction, oh rats, I should have made my mass 100. 1050 times 0.8. The maximum force of static friction is 840 newtons. And the maximum force of kinetic friction is, I'm just going to go to 3 sig figs, is 704 newtons. All right, so what time do I begin to move? So there's this transdimensional wormhole that exerts a force on me. Let's say the wormhole is over this direction. I don't know how you draw a wormhole. It's a wormhole. And it's exerting a force, and I'll stay in place as long as the force of friction acting this way is sufficient. When will I start moving? Well, when this force exceeds the maximum force of static friction. So if I just set this up, 840 equals 89.4 T plus 12.3. If you solve that very quickly, you'll discover that, oops, my calculator decided to bail on me. 840 minus 12.3 divided by 89.4, and you'll discover I will begin to slide at let's just call it 9.3 seconds. Force diagram just after I begin to move. So now what happens at that point? Well, at that instant, or just briefly by the instant, I have 840 newtons acting this way. And once I start sliding, I'm going to immediately switch to kinetic friction. So I only have 704 newtons acting this way. So my force diagram, unfortunately, I'm going to begin to accelerate very rapidly. My initial acceleration, just the difference between those, 840 minus 704, divided by my mass, 105. I'll discover that my acceleration is about, just using F equals ma, about 1.3 meters per second squared. A graph of my acceleration versus time for the entire event. So what's going to happen here? Acceleration versus time. Until I reach that 9.3 seconds, my acceleration is actually going to be 0. And then suddenly at this point, it suddenly jumps up to this 1.3 meters per second squared. What happens after that? Well, because the force is increasing linearly with time, what should happen? My acceleration will increase with time, something like this, where I got a little dot, 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 right here, until I reach that 1.3 at that time. Create a graph of velocity versus time for the inquired event. Well, how do you get that? You would have to integrate underneath this curve. So for the first part, pretty doggone easy. Until 9.3, my velocity is 0, because there's no acceleration, no air underneath the graph. And then from here, the area is increasing with time. So it starts out here at 0, but I'm accelerating. And it's going to increase somewhere. It's going to be some sort of a curve up like that. This last one is a little painful one. If the force is not dependent on the distance between the transdimensional wormhole and Mr. Clymer, how long will it take me to fall into this doggone thing? That's a little bit more challenging. How do I have to solve that? I need to figure out when the area underneath this curve is equal to 4 meters. And you might say, oh, well, I just need to, yeah. First of all, you have to write an equation for the acceleration based upon this force, but realizing that the force doesn't start acting until that time. You've got a discontinuity in here. Once you have that equation, you can find the function for velocity. And then once you have that, you can integrate to find an equation for position with respect to time. Just a quick note on this one. I would actually set the 0 time at the point where my velocity would start increasing. Otherwise, the mathematics gets really quite painful. And then figure out how much additional time is required before that becomes 4 meters. I'm not going to do F. If you want to try it for extra credit, you are more than welcome. I figure you need a little bit of an extra credit question. You do need to show me all of your work for this one. For this extra credit, just email it to me when you're ready. And, we got a conceptual question. Boring. All right, with that, I'm done for the day. Have a good night. Good luck with the homework questions. Ask me any questions about that or the lab. And we'll talk to you soon. Bye.